problem number 8 in group theory. Problem number 7 was a rough one, a harder problem. Problem number 8 is easier, in my opinion at least. It's just going to be first iso theorem is going to carry hard, and we're just going to use that to prove both A and B. So A says let phi from Z39 to Z7 be a non-trivial group homomorphism. What subgroups of S7 can be the image of phi? There are many, but they can be described succinctly. Okay, so let's just do our proof for part A, and by the first isomorphism theorem, that gives us that Z39 modded out with the kernel of phi is isomorphic to the image of phi, which is a subgroup of S7. Okay, so this is what we have from first iso theorem, giving us this guy, and essentially the idea is we're going to consider orders. Okay, so we have that. Okay, we consider orders, and essentially I want the same thing, but we know that the order of Z39 is just 39. The order of the kernel, I'm just going to put the order symbol around. Order of image, I'll do that same thing. I'll just put the order symbol around. And the order of S7, if you don't know, is 7 factorial. And instead of isomorphic, I'm just going to say equal to, so we're talking about numbers now. And even this less than or equal to, that could be like a divide symbol. It's probably more appropriate. Okay, but we want to think about this equation essentially. And maybe I even want to use a fraction here because I'm not talking about modding out now. We're actually talking about dividing this. Let's see how that looks. All right, yeah, that looks cleaner in my opinion. So we're saying that 39 divided by whatever the order of the kernel is going to be equal to whatever this order is. That has to divide 7 factorial. And I really like thinking about divide better than less than or equal to. Okay, so our possible orders of the kernel are 1, 3, 13, and 39. We can rule out 39 since our homomorphism is non-trivial. So that's 1 eliminated. And further, we can rule out 1 because 39 does not divide 7 factorial. We could also rule out 3 because 13 does not divide 7 factorial. And that leaves us with just 13, which is 3, which definitely does divide 7 factorial. Further, we can rule out 1 and 3 since 39 and 13 do not divide 7 factorial. Hence, the order of the kernel of phi is equal to 13. And so the order of the image of phi, I spelled operator name wrong. I should just bind this. Okay, the order of the image of phi is equal to 3. And subgroups of S7 that have order 3 are the 3 cycles. 3 cycles that look like this. And since they have order 3, we can say that the hence, or I'll say thus, I just used hence, thus the cyclic what am I doing? Thus, the cyclic subgroups that look like this are angle are, okay, I see where I went wrong. I should say elements here. Elements. Elements of S7 that have order 3 of the cycles that look like this, thus the cyclic subgroups that look like this. Sorry, thus the cyclic groups generated by these elements are the subgroups of S7. And we could also say that this is isomorphic to Z3. So that can be the image of phi. Okay, so this is part A finished, and part B we're going to use, let me begin a proof environment. We're also going to use first isotheorem again. The difference is the map is now kind of flipped, and we're proving that there is no non-trivial group homomorphism psi that goes from S7 to Z39. Okay, so we'll consider, or maybe we'll assume there exists a non-trivial group homomorphism psi from S7 to Z39. And then we'll contradict why this can't happen, why there cannot exist a non-trivial homomorphism from Z7 to Z39. Okay, by the first isomorphism theorem, we use that again. We have that S7 over modded out with the kernel of psi is isomorphic to the image, I spelled operator name, there we go. Image of psi, which is a subgroup of Z39. Okay. Okay, it finally compiled. I had to turn off autocompile there. I'll turn it back on, see if refreshing it fixes it. Okay, so we have this relationship, and so we're going to kind of do the same thing that we did with part A, where we consider orders, but even before that, we can say something. We have that the kernel of psi, so we know that the kernel of psi is a normal subgroup of S7. And a known fact is that for the symmetric group like Sn, for n greater than or equal to 5, the only normal subgroups of Sn are An, the trivial subgroup with the identity, and itself, so Sn. Okay, so we know the only normal subgroups of Sn are, I'll just write out what I just said, that guy, A7, and S7 itself. We can rule out S7, okay, sorry, we can rule out the kernel of psi equaling S7 since we have a non-trivial homomorphism. If the kernel of psi is equal to the trivial guy, then we want to contradict this, so then we have that S7 is isomorphic to the image however, the image, which is a subgroup of Z39, however, if we consider orders, 7 factorial does not divide 39, since it has to, by Lagrange, it has to divide that 39, but it in fact does not. 7 factorial does not divide 39. Hence, the kernel of psi is definitely not the identity. The identity subgroup. Okay, so then our only other normal subgroup is A7. If the kernel, whoops, not in math mode, if the kernel of psi is equal to A7, then S7 over modded out with A7. So the symmetric group and the alternating group is half, is essentially, it's all the even permutations, so it's half the subgroup. So this is isomorphic to Z2. Sorry, Z2, like that. Okay. Hence, the order of the image of psi is equal to 2, but similarly, 2 does not divide 39 by Lagrange, it has to divide it. Therefore, there does not exist a non-trivial group homomorphism psi. And that concludes B.